It's the month of the comets as we track 4 of them traveling through our solar system.
Aliens paying us a visit from another star system? What's up with that?
An amateur astronomer noticed something unusual in solar observation data, a faint smudge moving through space. That smudge turned out to be a brand new comet heading our way that we're now calling Comet R2 Swan.
Something massive just erupted near the sun. A flash, a shockwave, and now Comet R2 Swan is racing toward Earth fast. Overnight, its brightness exploded. One moment it was a faint blur, the next, a blazing streak cutting through the darkness. Its tail now stretches wider than 5 full moons, visible even in small backyard scopes. Observers everywhere are stunned. No warning, no buildup, just sudden ignition. And then, as if the universe wanted to raise the stakes, the sun fired back, unleashing its most powerful flare in months, aimed straight toward Swan's path. What happens when solar fire meets a runaway comet? We're about to find out. The timing could not have been more uncanny. Solar physicists scrambled to confirm the flare's path, while comet observers whispered the same thought. Two forces, one blazing with fire and one fragile with ice, were on a collision course through the same corridor of space. No one could say what would happen when a billion-ton wave of plasma struck a crumbling nucleus of dust and frozen gas. For the moment, there was only motion. Swan was accelerating, brightening, and behaving like no comet on record. By mid-September 2025, the numbers told a story that refused to stay predictable. Swan had rounded the sun at only half an astronomical unit, closer than Mars ever comes to Earth. It should have dimmed after passing perihelion, but instead it exploded in light. Its magnitude jumped from 7.4 to 5.7 in just a few nights, bright enough for the naked eye under clear skies. Amateur astronomers in Japan and Australia first caught the flash on September 26th, a sudden bloom that turned faint haze into a brilliant streak. Within hours, international forums filled with images and photometry data. By the time professional observatories verified the spike, Swan had already forced telescope teams to rewrite their schedules. What began as a quiet smudge on digital sensors had become a worldwide phenomenon. Swan entered what astronomers called a hyperactive phase, a runaway chain of heat and gas venting into space. Every new frame showed change. The coma swelled, the nucleus flared, and the halo grew with each orbit of sunlight. It no longer behaved like a passive traveler. It pulsed like something alive. The reaction deep within had broken through its crust, turning the comet into a furnace of ice and dust. Beneath its fragile surface lay frozen reservoirs waiting to ignite. When sunlight finally reached deep enough, the pressure shattered the crust. Jets erupted like geysers, launching dust thousands of kilometers into orbit. Swan had crossed a threshold. It was no longer a faint wanderer, but a cosmic spectacle, roaring through the solar wind as its glowing plume carved a luminous scar across the void. Telescopes began detecting asymmetric plumes, fans of material streaming in uneven directions, proof that parts of the surface were collapsing while others still held firm. Each outburst fed the coma, swelling it further and fueling the tail's expansion. Light curve data taken night after night showed the same steady climb, a curve that refused to flatten. Astronomers knew what they were seeing, a world unraveling in slow motion, its icy skin boiling away under the relentless heat of the sun. Every observation became a piece of a puzzle still being assembled. The color changes, the shape of the jets, the shifts in brightness, all pointed to complex chemistry at work. Molecules torn apart by sunlight produced faint glows in blue and gold, the signatures of ionized carbon and dust scattering reflected light. For the scientists, it was an opportunity. For casual observers, a spectacle. Swan was no longer a quiet traveler. It was a living experiment in the physics of heat and ice, unfolding before human eyes. As the eruption continued, the comet's tail expanded into one of the most striking sights of the year, stretching nearly 2.5 degrees across the sky, 5 times the width of the moon. It became visible even through binoculars. The two distinct tails told different stories. The golden dust tail, shaped by gravity and sunlight, and the electric blue ion tail sculpted by the solar wind. Together they formed a portrait of motion and instability, a painting on the canvas of the night. Observers across continents compared notes. From Australia to Chile, time-lapse sequences revealed knots and kinks forming and dissolving within hours. Jets of gas would flare, then fade, replaced by new streamers angled in unpredictable directions. Even modest backyard setups captured the changes, while professional arrays stitched hundreds of exposures into composite frames that showed the tail bending and twisting like a ribbon in a solar breeze. The global comet community came alive in ways rarely seen. Online groups buzzed with data sharing, software overlays, and field reports from every hemisphere. Amateurs stacked exposures, comparing brightness across nights, while larger observatories filled in the missing pieces with spectroscopy and high-resolution imagery. Swan had become a classroom without borders, a real-time demonstration of how sunlight, dust, and plasma shape the most fragile bodies in the solar system. But the spectacle above was only the beginning. On September 28th, the sun itself entered the story with a display of power that shifted every calculation. At 8:43 Coordinated Universal Time, solar observatories recorded an M6.4 class flare erupting from active region 4232. For weeks, the sun had been quiet, its X-ray flux flat and uneventful. Then, without warning, its brightness surged. Instruments on the GOES satellites spiked. The flare blasted out a coronal mass ejection traveling nearly 900 kilometers per second, fast enough to cross the distance between Earth and the Sun in less than 2 days. Inside the Space Weather Prediction Center, analysts traced the path and froze. The expanding wave was not Earth-directed, but its projected corridor intersected the very region where Comet Swan was now moving. The geometry was almost too precise. A solar storm, a newly awakened comet, both aligned in the same quadrant of space. For scientists, it was the setup for a natural experiment that no lab could ever replicate. Modeling teams at NOAA, NASA, and the European Space Agency began plotting trajectories in real time. Data poured in from the Solar Dynamics Observatory, from SOHO's coronagraphs, from the twin STEREO spacecraft positioned on opposite sides of the Sun. Each image confirmed the same conclusion. The coronal mass ejection's leading edge would sweep through the comet's path within 48 to 72 hours. This was not a theoretical encounter. Swan's enormous tail, millions of kilometers long and charged with ions, would soon meet the turbulent magnetic front of a solar eruption. The plasma's embedded magnetic field could snap the comet's ion tail like a thread, triggering a rare tail disconnection event visible even through small telescopes. The physics were brutal and beautiful. A stream of charged particles from a star colliding with the delicate filament of a frozen traveler. An interaction played out across space in real time. Forecasts now show the coronal mass ejection moving fast and wide, a storm of charged plasma expanding through interplanetary space. Within 48 to 72 hours, it will sweep through the region where Comet Swan glides, trailing its enormous tail behind. Every solar observatory on Earth, has turned its instruments toward that corridor. Analysts trace the CME's shape frame by frame, watching as it twists, fragments, and spreads across millions of kilometers. It's a living wavefront of magnetic turbulence, the kind of phenomenon that can swallow spacecraft, distort radio signals, and shred the delicate ion tails of comets in its path. Inside control rooms from Washington to Brussels, space weather teams issue alerts. Not for danger to Earth this time, but for the opportunity. The forecast is a direct hit on Swan's neighborhood, a natural laboratory unfolding in real time. Comet researchers, heliophysicists, and amateurs alike brace for impact, their telescopes trained on the faint blue filament that may soon snap apart. This is not speculation. It's a countdown measured in hours, and the stage is set for one of the most dynamic displays of comet physics in years. If you want to stay ahead of every update and witness history as it unfolds, make sure to subscribe now. The CME, traveling nearly 900 kilometers per second, carries more than heat and light. It drags magnetic field lines twisted into vast spirals, each one millions of kilometers long. When those lines meet the charged ions flowing from Swan's nucleus, something extraordinary can happen. Scientists call it magnetic reconnection, a brief but powerful event where magnetic fields collide, break, and reattach in new configurations. It's the solar system's version of a power surge, converting magnetic energy into motion and light. If the CME's embedded magnetic field points southward, opposite to the direction of the comet's local magnetic flow, the effect can be explosive. In seconds, the ion tail can disconnect completely, a section of glowing plasma drifting away into space while a new tail begins to form almost immediately. Cameras will see it as a sudden kink, a drop in brightness, or a detached arc glowing faintly as it floats behind. For those watching through telescopes or tracking spectra, the signs are unmistakable. Hydrogen and oxygen lines will shift, rippling across wavelengths as the plasma reacts to the shock. It's not just theory. Similar events have been caught before, most famously in 2007 when a coronal mass ejection severed the tail of Comet Encke. But this time, the circumstances are different. The comet is brighter, the sun is near its maximum, and the world is watching together. Every observatory from the ground to orbit has a role. NASA's Solar Dynamics Observatory follows the solar side, while amateurs on Earth document the comet's reaction. For the first time, a tail disconnection event could be mapped almost continuously from multiple vantage points. October 21st becomes the key date. On that night, Swan will make its closest approach to Earth, roughly 39 million kilometers away, or a quarter of the distance between the Earth and the Sun. It's a near pass by astronomical standards, close enough for the comet's delicate structure to be studied in unprecedented detail. The timing is almost poetic. At the same moment, Interstellar Visitor 3 I/ATLAS will reach superior conjunction, hidden behind the Sun from Earth's view, but geometrically aligned with the same corridor of space. Two cosmic travelers, one local, one from beyond the stars, crossing paths in the same week. The viewing conditions could not be better. A new moon ensures deep darkness. The comet's path along the southern sky favors wide visibility, and telescopes in both hemispheres are poised to capture every change. NASA, ESA, and JAXA coordinate observation campaigns with citizen scientists through online networks. Discord groups and astronomy forums turn into real-time command centers, sharing exposures, timestamps, and positional overlays. Each frame adds to the global mosaic. Every observer, whether under suburban skies or remote mountain peaks, contributes to the collective record of a once-in-a-generation encounter between sunlight, plasma, and ice. From Buenos Aires to Perth, dawn skies glow faintly with anticipation. Swan rises early, its long tail stretching across the southern constellations, a luminous streak visible even through binoculars. In northern latitudes, observers wait until after midnight, watching it climb just above the horizon. As October progresses, the comet gains altitude each night, the tail turning and shifting with the planet's rotation. The geometry allows for something special: measurable parallax. At just 0.25 astronomical units away, Swan's apparent position changes slightly depending on where you stand on Earth. Teams in different continents measure that subtle shift, comparing images taken hours apart to refine its distance and motion. It's a rare moment when amateurs can detect the scale of space itself, the slight wobble revealing depth in the night sky. Some use simple cameras on tripods, others deploy observatory-grade optics, but all share a single goal: to document the comet as it dances with the solar storm. The checklists are simple but vital. Record the time, note the comet's position, capture the tail's orientation. Look for sudden brightening or fading, for kinks or breaks that signal magnetic reconnection. Even a casual observer can contribute. In a networked age, thousands of small observations combine into something greater, a data set rich enough to study the physics of plasma flow on an interplanetary scale. The excitement isn't limited to professionals. This is a scientific event powered by curiosity itself.